Okay, let's talk about boundedness of a sequence. What does it mean for a sequence to be bounded? First, we look at two things. A sequence is considered to be bounded above if there exists an m such that a sub n are less than or equal to this m for all n bigger or equal to 1. Now, what does that mean? It just simply says that all the terms of your sequence, whatever they are from the beginning until the end, going on infinitely, of course, forever, they're all going to stay below this one number m. So there's going to be sort of this, you can think of it as a cap above that doesn't let the terms of your sequence go beyond this value m. So everybody stays below m. That would be the sequence is bounded above by this m, which of course doesn't have to be unique. A sequence is bounded below if there exists an m such that a sub n, all the terms of your sequence, are always bigger than this value m. So from the beginning until going on forever and ever, they always stay above this value m. And so you can think of this as you have a cap below for your sequence. So in the first case, bounded above means you got, think of it like this, some big M, and all the terms of your sequence are below it. And in the second case, you've got maybe some little m, let's say here, where all the terms of your sequence are staying above that value. So for the first case, big guy above, everybody stays below. Second case, little guy below, everybody else, all the terms of the sequence stay above it. And then finally, if the sequence is bounded above and bounded below, the sequence is considered bounded. So basically you can think of it as some guy below and some guy above, and then all the terms of your sequence, wherever they are, they always stay above the little guy and below the big guy. If that's the case, then your sequence is considered bounded. Let's go look at a couple of examples. So the question is this sequence bounded below, bounded above, and finally, is it bounded? Well, let's just take a look at the terms of the sequence. If n is 1, I have a sub 1, which is 2 times 1 minus 1, that's 1. If n is 2, I have a sub 2, which is 2 times 2 minus 1, that's 4 minus 1, which is 3. A sub 3 looks like it gives me the next odd number, and so forth. So if I'm looking at the terms of my sequence, I can see that these are simply just the odd numbers that it's spitting out. And as I go on, the odd numbers, of course, are going to get bigger and bigger. And is the sequence bounded above? Well, this goes off to infinity. So for above, my answer would be no, because it blows up and it goes to infinity. Is the sequence bounded below? Well, it has to be for all n, and I can look at the terms of the sequence and say, well, I started with 1, then I went to 3, then I went to 5, and so forth, and all the terms of the sequence, of course, got bigger and bigger, but at the bottom, you could say that there is a bound below because none of these guys go below 1. So if you would like, you can say, yes, it is bounded below, and you can give any number that's either 1 or smaller than 1. So we can say bounded below by 1, because everything is bigger or equal to 1. You can even say by 0.5 if you want, by 0.4 if you want, by 0 if you want. The point is, it is bounded below. And in this case, since everything is bigger than 1, I could even use that very first term and say it is bounded below by 1. Again, what it's bounded below and above by doesn't have to be unique, it just has to be bounded. So in this case, that's a yes, that's a no. So obviously, is it bounded? The answer would be no, because for it to be bounded, it has to be bounded above and below. Is this sequence bounded below, bounded above, and bounded altogether? So again, we're looking at a sub n, n over n plus 1 as our sequence. We can go and spit out a few values by hand and also look at our ti, so if n is 1, I have 1 over 1 plus 1, which is 2. If n is 2, I have 2 over 2 plus 1, which is 3. If n is 3, I got 3 over 4, and so forth. Let's also go review how to put this into our ti. So I'm going to go to mode and make the mode enter for sequence mode. Then if you go to y equals, quit that, go to y equals, oh, hasn't worked. Okay, let's try again. So I'm going to go to mode, sequence, enter, and then get out of that screen. I have options. I can either go to second, stat, ops, and then choose 5 right here for sequence. And then put this guy in. So my sequence is n. You go where x used to be, divided by n plus 1. Comma, in terms of n, comma, from 1 to whatever you want. Let's say I want it from 1 to 10. And then comma, the last one should always be 1. That's the step, so that means every 1 you go up and you spit out the values. And you can push enter. And if you look through your list, it looks like it's an increasing sequence because the terms keep getting bigger and bigger. That's what the pattern shows. And I can also go look at this where I used to input functions. I can put n divided by n plus 1. And I can look at the graph. So my window was nice there. My window was from 0 for x min, x max 10, 0 to 5 for my y. So if I look at the graph, it shows me the terms of the sequence, and I can see that they're getting bigger and bigger. And also notice my y value went up to 5, so it seems like right here they're getting closer and closer to 1 as we would suspect. Another thing you can do is second graph, and that should give you a table with all the values. So you can just go through your table from 1 on and see the pattern of what's happening. Notice as we go down, the terms of the sequence are getting bigger and bigger and staying under 1, it seems like. So you can use your TI to explore that. The point is, though, is it bounded below and above is what we want to look at. And as we saw, it seems that the very first term was a half, and then they got bigger and bigger as we went through the terms of the sequence. So we can say, yes, this is bounded below by a half, let's say. You can say by something smaller, but the very first one was a half, and then from there on they kept getting bigger. So below there is something smallest you can choose. You can say, yes, it's bounded below by a half. Now, is it bounded above? Well, as you noticed, as we go through the terms of our sequence, it doesn't seem like they get past 1, and that makes sense too. And looking at the graph too, they're getting bigger and bigger, but it doesn't seem like they're going off to infinity. Looking at this also, it makes sense because the denominator is always bigger by 1 than the numerator, so it makes sense that this guy is not going to get bigger than 1. So is it bounded above? You can say yes, and you can say it's bounded above by 1, let's say. And again, I say let's say because you can say it's bounded above by 2 if you'd want. Like, it doesn't have to be unique. Now, is it bounded period? It's bounded below and bounded above, so your answer is yes. Basically, you're saying that n over n plus 1 is always bigger or equal to a half, because that's the smallest guy it can be, and it's always less than or equal to 1, because that's the biggest it can be. So this leads us to a theorem that connects boundedness and how a sequence that's monotonic can be concluded to converge if it is also bounded. The theorem basically says that every bounded and monotonic sequence is convergent. In other words, whether you can find what the value of the sequence converges to or not, if you can just show that it is bounded and you can also show that it's monotonic, remember monotonic means either increasing or decreasing, and bounded basically means there's a cap below and a cap above. If you can show these two things, then you can automatically conclude that the sequence will be convergent. Now, why does that make sense if you think about it? Let's say we have the terms of the sequence and it's supposed to be bounded. So there's an M below and a big M above. So they're bounded, first of all, is the first criteria. And then it also has to be monotonic, so your sequence can only increase or it can only decrease. So the terms of the sequence basically does this. Well, if it does that and it's bounded, it has no choice but to converge to something because it keeps increasing. Or if it's monotonic and it's decreasing, you have your terms of the sequence that go like this. So eventually, they have no choice but to converge to some lower value. It basically gets trapped. Every bounded monotonic sequence causes your sequence to creep up and converge to something, or just go down and converge to something. So let's use the theorem above to analyze the convergence of the sequence, or maybe the divergence of it. So this we looked at in class, and we showed that it was monotonic. Again, we said we had two options, either show for any two general terms next to each other or find the derivative. Let's go quickly look at both of them. So for first question, let's say if it's monotonic or not, see if it's increasing or decreasing and show it. It looks like the first term is a negative, and then from there on, the terms keep getting bigger and bigger, so we're suspecting that this is maybe an increasing function or increasing sequence. And we want to actually go formally show it. If I'm formally showing it, my next term better be bigger than my current term that I was standing at, so this must be true. So we replaced all the n's for our a sub n with n plus 1, and we're just going to go do some simplification. So now we're here, we're still not clear whether this guy really is bigger than that guy, so we're going to multiply both sides by the LCD, and again we can do that because this is positive and this is positive, so it's not going to flip the inequality. So we got rid of the denominators, we multiplied the two binomials out, and now we can see that in this inequality, these guys disappear, and we end up with negative 4 is bigger than negative 21, which is true in this case. So for two general terms that were next to each other, a sub n plus 1 and a sub n, we showed that this guy is bigger than that guy, and so we've proven that that will be the case for all n because we got a true statement. Alternatively, remember, we can also show that comparing it to a function. So I can say compare the sequence that I was given to this function, and let's go analyze the derivative because the derivative tells us about the increase and decrease of a function. So if I compare it to this function and use the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top, do some simplification and notice what we get for f prime. This guy is 17 is always positive, the denominator is always positive. So this is positive for all x bigger or equal to 1. That's all I care about because my sequence starts at 1. Of course, there's a place where this is not differentiable, but that happens when x is negative, and I don't care about that. So this guy is always positive, so your sequence is always increasing, just like you showed for this general case comparing two terms next to each other. Using the derivative, you can also show that this sequence is always increasing. So let's use the theorem above. Let's go see what we did. We showed that it was monotonic. We just have to show that it is bounded, and then we know for sure that the theorem says it's convergent. And we can actually even find that limit. So we're just applying the theorem